One of the methods to make alcohols is alkene hydration. So let's just draw an alkene here. And hydration means, as the name says, adding water. So you will add each NOH across the double bond. And we will have different conditions in different outcomes on that. First, let's review the Markovnikov hydration. So if we have that alkene, and now, as we said before, we're gonna, well, typically we will have reagents for. Let's list those first. The Markovnikov hydration, essentially you will add the H at the least substituted carbon and the OH at the more substituted. That will lead to the formation of the following alcohol. So conditions to do that, well, depending on the structure of the alcohols, but in first place, we can use, say, simply hydronium. You may see this also written as some diluted sulfuric acid and so forth. That will proceed via Markovnikov. Another condition to do the Markovnikov hydration is doing mercuration-demercuration, and we use this condition when we want to prevent a possible rearrangement of the carbocation. So let's do first this in mechanistically speaking, reviewing that again. And this, you first do that in mercuration-demercuration. Second step is sodium boron hydride. Okay, that will do a Markovnikov. This is the outcome of that. So how that happen? Well, if you had, say that, let's just draw explicitly the 3 hydrogens in hydronium. So we have, I say the conditions. Then you will have the here pi electrons acting as a base, so a proton transfer step in which you're going to, here as a product of that, the H is going to be added at the least substituted carbon, and you will form, in this case, the following carbocation. Again, H was added here. That's a tertiary carbocation. So the reason this reaction proceeds, like we said, the Markovnikov rule being the H at the least substituted, is because that way we make the more stable carbocation. If we if the hydrogen was here, then you will have a primary carbocation, which is very unstable. So that's what we have in the first step. And in the second step, we'll simply have water. This is diluted acid. So water will be your nucleophile. Right, so, and after another proton transfer step, you will get that alcohol, a tertiary alcohol. Now, I'm going to give you another structure of why do we use the other condition that we have here, mercuration-demercuration, because we just mentioned that we get alcohols in this pathway under acidic conditions producing a carbocation. If the carbocation that is produced is not tertiary, for example, something that's not stable, it may rearrange. So the reagent that we have for mercuration-demercuration actually prevents that rearrangement. So now I'm going to draw another structure here, and that is, okay, so now I have this. Okay, with that, that's another alkene. Say that I have that, and let's draw, now I'm gonna draw hydronium in a different way. And it's the same thing, it just have 3 hydrogens attached to the oxygen. Oxygen has formal positive charge. If I do that, now I'm gonna form the following carbocation. You remember that Markovnikov pathway, you will add the H at the least substituted carbon, which is actually that terminal carbon. That would lead me to the following, right? Not very good. It is a primary carbocation. But we can have a better carbocation here. And that is, we can do, I'll that's not a good example. Take it back. I'm going to cut the video right here. Gracias, horror. We talked in a previous video about methods of making alcohol, and that one of them is alkene hydration. Alkene hydration can happen via Markovnikov using these reagents. We use diluted acid when there is no, say, we don't have the possibility of carbocation rearrangement, which is an intermediate in the Markovnikov hydration. So, and we said that, for example, if we do the Markovnikov hydration in this particular case, would lead me to a tertiary carbocation, so which is stable, no need for rearrangement. But what if the structure is different? So this is what we're going to talk about. When do we need to use the other reagent, which is for mercuration-demercuration? So now I'm going to have the following structure. And I'll say that I'm using this condition for Markovnikov hydration. If I have that, and now I'm going to draw hydroning in a different way. So there's several ways you can do that, but if I did here, one drawing that we do often is this. And you will have, say, a proton transfer step, pi electrons acting as base, and that would lead me to hydrogen being attached in here, the least substituted, and will form a tertiary carbocation. That's the Markovnikov pathway. Now I'm drawing hydronium different than that, but it's the same. So and now pi electrons again acting as a base. What are the parts? And see what we form now. If we do attach the hydrogen at the least substituted, we are going to have the following structure. That is a secondary carbocation. That was tertiary. So not too stable. But this carbocation may rearrange. So we can do a 1,2 hydride shift. In hydride, you're migrating this hydrogen with the electrons at the bond. That's why we call that hydride. So we're going to do this migration. And it's 1,2, so the atom that is right on the side, say. So what is the product of that? So after we do the migration, we're going to have the following. Now the hydrogen is going to go here, and you're making a tertiary carbocation. So if your target molecule was that, you're not going to get that product from this. So, well, in other words, if you wanted, I didn't say it right. So this is from that. Now, if you wanted the alcohol coming from this carbocation, which will be this, you're not going to get it because this carbocation, being secondary, is not as stable. So you will have a 1,2 hydride shift in the final product will be this alcohol instead of what I wanted. So I wanted to make that. It's not going to happen using this reagent. So that's when we use the mercuric acetate. And then you do mercuration-demercuration. And we are preventing the rearrangement because, and I just want to throw the intermediate for that. We are forming what we call a mercurinium ion. And that mercurinium ion, so if we use, say, that substrate that we have here, and now let's do if that with mercuric acetate will form the following. So let's do that bold lines like wedges. There's mercuric acetate, that's formal positive charge here. So that intermediate in this reaction does not rearrange, it prevents rearrangement. And now you're going to have the attack of, say, your nucleophile being water. Well, actually, the mercuration is done in water, will produce an alcohol. You can also do other reactions to make ethers if you have, for example, methanol here. But now, if your attack was water, this will open up and you will get the alcohol you're interested in. So you will have the OH here as we have in the product. So again, wrapping up, conditions for alkene hydration. If we want the Markovnikov alcohol, we have two options. We can do the diluted acid if we don't have possibilities of rearrangement, or if we do have that and we don't want the rearranged products, such as in this case, we don't want that product, if we want that, then to prevent it, we use the mercuration-demercuration.